Thank you for introduction, and thank you for giving me the chance to talk the first. So I'd like to share the D graph. Can you see the PDF file? The first page of the PDF?
Yes, I see.
Okay. Okay. So if my voice is not clear, please don't hesitate to say so by microphone anytime. Maybe I cannot hear my voice. So let's start my talk. So maybe the title of today's talk is very strange. Why the precision of TXRF quantitative analysis is so bad? So this is, I seek some words. It's a tacit knowledge. This is Michael Polanyi's words, but if you don't know the tacit, I also don't know these words. So it's a layperson's words. It is translated as wordless understanding, or it's just like many kinds of, how to say, it's laboratory knowledge of experiment. So I'd like to share something like such kind of thing in my first lecture. So there are many factors to prevent the precision of TXRF quantitative analysis. And it is common to ICPAES and wavelength dispersive XRF and XPS, micro XRF, SEM-EDX, or EPMA, or scanning tunneling microscope. So there are many problems. There are many methods common to the same problem. And I'd like to explain from the first one to the 10th. The amount of specimen or a beam size is a big factor for the precision of the quantitative analysis. And also the energy dispersive detector or spectrometer or digital signal processor is also a factor. And sampling, of course, it's a big problem. For example, a ship of iron ore is imported to the shipyard. Then the sampling from such kind of large amount to the small amount is very difficult. And thickness, density, or critical angle. This is the case of total reflection X-ray fluorescence. These are very important problems. And the surface roughness or inhomogeneity, and peak and background, escape peak and some peaks. And also, I think the synchrotron radiation is a big problem. Though this is a very good X-ray source, but at the same time, we have a big problem. And electric circuits, and also we accept the bad precision. So we think the bad precision of TXRF is a matter of fact, and we give up the improvement. So I'd like to start from the synchrotron radiation. So the problem of synchrotron radiation is that the beam is too small. So you can see here many kinds of X-ray fluorescence samples. And to compare the size, to know the size of the samples, I put here the NW25 vacuum flange. So its outer size is 40 millimeter diameter, and the hole here is 25 millimeter. So the sample size of X-ray fluorescence is usually 40 millimeters or more, or sometimes about 1 inch diameter, and at least for XRF quantitative analysis, at least 1 inch diameter is needed. So the laboratory X-ray fluorescence, wavelength dispersive X-ray fluorescence, the sample is sometimes rotated. So such kind of mechanism is in the sample holder. But the synchrotron radiation beam size is too small. Sometimes it's nanometers and micrometers, and at most a few millimeters. And synchrotron radiation intensity is it's too strong and therefore not stable. And this kind of briquette, it's made of powder, and when we want to make this kind of briquette, at first the powder mesh size should be controlled, and then the pressure, increasing or decreasing the pressure, is also well controlled. So this kind of thing is very important for the quantitative analysis. Also, this is the sample carrier. It's a quartz plate, and we have checked this square type or disc type, and we found the square type is better than disc type, because the incident X-rays scattered at the edge of this around here, and it will make worse the X-ray intensity. So next, I'd like to say the surface roughness. So it's back to my memory just 40 years ago when I was a bad student. I'm not a good student, and I'm still a bad researcher, as you know. So when I was a student, the instructor of university experimental experiment give 6 students. All 6 students measures is analytical chemistry. He gave us the roasted iron or steel standard sample. And then he ordered us to polish the surface by a rough sandpaper, then intermediate sandpaper, and finally, I'm not sure, maybe 900 or something sandpaper to finish the surface. Then we measured we make the calibration curve using the iron and the steel standard. This percentage range is very narrow, maybe 5% or less, very narrow range, and XRF intensity is also very narrow. If you use EDX, energy dispersive X-ray fluorescence, all these 6 points are the same. But except for me, other students followed the instructor, and they polished at first rough polish, then intermediate, and finally fine polished. But I was a bad student, so I omitted the intermediate. Only the rough and the fine sandpaper I used. Then finally we plotted the X-ray counts, and the instructor found my point was it's an outlier, just like this, and he said to me, maybe you omitted the intermediate polishing. So it was correct. So because I was a bad student, I understand the surface roughness is very important for the precision of wavelength dispersive X-ray fluorescence quantitative analysis. So next one is also the synchrotron radiation XRF, but wavelength dispersive XRF. So this I plotted from the already opened forensic report 3 set of data into one graph, just like here. And the first one, this x-axis is the sampling was 1998, and ICPAES was measured in 1998, and arsenic concentration was determined. So A and B is 75% or something, and C and D is 60 to 70%, and E is about 50%. So in 1998, Dr. Marumo determined the arsenic percentage. And then 2001, another researcher, Watanabe, sampled again from the same evidence, and he measured Parkin-Ehrman ICPAES, and he measured only molybdenum concentration as an impurity in arsenic acid. So molybdenum impurity was from maybe 30 to 70 ppm. And arsenic is from 50% to 75%. So as you can see here, the 5 evidences lined on the same, this straight line, and this is the least square fitted line. So A, B, C, D, E originated from the same roots or same source. But at the same time, Hayakawa measured using the wavelength dispersive X-ray spectrometer at the spring 8 beam line. So X-ray is coming here, and here is the sample, and the X-ray fluorescence was analyzed by the crystal and then detected by the scintillations counter. And the samples is just like this. Its diameter is 5 millimeter, and the beam spot size is maybe 1 millimeter or something like that. Then the concentration of molybdenum was scattered like this. So from the spring 8 measurement, it is not possible to conclude whether A, B, C, D, E come from the same roots or not. So we recognize that the sample size or beam size is too small. Then the quantitative results are not reliable. So this is another example how large amount should be sampled. If we want to analyze 50% or if we want to analyze 50 ppm. In the case of STM, scanning tunneling microscope. So this is the Monte Carlo simulation results. So, for example, the silicon surface is made of silicon atom, and 50% is made of other elements. So maybe 100 atoms are silicon, and 100 other atoms, rest atoms are other elements. So in that case, if we measure only 10 atoms, then it is scattered like this, and 100 atoms, then the divergence is a little bit smaller, and finally the reliable 50% can be obtained unless we measure 10,000 atoms on the surface. So the procedure to measure or to estimate by the Monte Carlo simulation is just like this. at first produce 10 random numbers between 0 and 1 million, between 0 and 1 million. It's an integer. Then count the times when the random number is less than 50. So in this case, it's here. Oh, this one. This is 50. I'm sorry. This is 50 ppm. But so I'd like to explain afterwards. So in the case of 50 ppm, so it becomes 10 to the 8th atoms. That means we must measure 10 to the 8th atoms. Then we can determine quantitatively the 50 ppm. So that the method is just I try to start to explain. So they produce 10 random numbers between 0 and 1 million and count the time when the random number is less than 50. This means 50 ppm. And then produce additional 90 random numbers between 0 and 1 million. Then count the time again, less than 50. So at first, if the 10 random numbers, it's 0, and 100, 0, and 1,000, 0, and it's 10 to the 6th, it becomes very close to 50 ppm, but still scattered. Then if the number of random numbers becomes 10 to the 8th, then we can determine the 50 ppm. So maybe it's not feasible using the scanning tunneling microscope to count the surface atoms 10 to the 8th atoms. It's not possible. So this is also applicable for ICPAES. The powder of 100 micrometer diameter, then we must analyze at least 25 250 milligrams of the powder if we want to know the larger than ppm concentration. And this amount is depending on the concentration. So this is also applicable to the TXRF. And if we want to discriminate 49 and 50 ppm, then we must count 10 to the 10th, something we can discriminate. So if we want to analyze more precisely, then the sample amount should be much larger. As an example, this is the instruction of the National Institute for Environmental Studies in Japan and the standard certified reference material of human hair. So the 3 grams of the human hair powder, less than 100 micrometer, was individually packed in acid-washed borosilicate bottles. So it is distributed just like this, but the minimum samples of the minimum sample amount should be 120 milligrams or larger. Then this certified value is it's possible. And so if you do not waste the sample and only 10 milligrams, then you cannot get this certified value. I'd like to change another topic. It's energy dispersive detector. So this is taken from the paper of Tibor Papp and others about the quality assurance challenges in X-ray emission-based analysis. So he compared two type of silicon lithium detectors. So the number one detector, its a response is just like this, and the number two detector is just like this. So all the detectors has its own characteristics, and this is a big problem when we use the energy dispersive detectors. So this is also based on the public document. The data is open for in public, and there are 25 spectra is overlapped. So that means arsenic oxide 25 cans. That means 25 rods. So lot number is from 1 to 25. The arsenic oxide was measured. Then this is measured at spring 8, and the germanium detector was used. So as you see, the peak intensity is changed when the rod is changed. But all the 25 rods, 100% arsenic acid. So this intensity change is because of the intensity, synchrotron radiation intensity change, and it can be normalized. But as you see here, the peak is shifted to low energy side. So this type of effect is very difficult to correct. So this is the reason when we use germanium detector, we must check maybe quite frequently, such as once in a day at least. The same sample should be measured to check the reproducibility. And this is another example. So this is a vanadium spectra, and we want to measure the low energy tail. So vanadium spectrum was monochromatic and by a crystal. So this is, we avoid the incident X-ray beam. We use the mega electron volts helium ion. And the helium ion bombarded the vanadium sample, and then this is a pixie. So X-ray is emitted and directly measured by a silicon lithium detector. So this is this dotted spectrum, and you can find K beta line and K beta escape peak and K alpha peak and K alpha escape peak here. But here is some low energy tail, and if the helium ion is bombarding the sample, and here is a solar slit, and analyzing crystal make it's monochromatic, only vanadium K alpha, and then detect it. So this is the response function of the, this yellow spectrum is a response function of the, how to say, single monochromatic X-rays. So we must know this kind of things before experiment. It's very tedious. So I'd like to say something more about the electronics. So this is a function generator to generate this kind of electric pulse, and the concentric electric cable is 1 meter length or 5 meter length. And if you use 1 meter length, it's quite clear if we measure using the oscilloscope. But it becomes longer, then some kind of ringing here, and This is because some kind of faults in the electric cable. So we must use terminator to prevent such kind of thing. But before that, we must repair something wrong place. Maybe some electric conductivity is maybe different, or the impedance was not regular. So this is another example for different cables and different rings. It's connected. Then without terminator, we found here the reflection signal at some impedance unmatched place. But if we use terminator, no reflection. So this kind of thing we usually do not check, but it's very important. Also, the undershoot is a big problem. So to compensate the undershoot, we in the analog circuits, we use this place. It's a pole zero adjustment screw. So this kind of thing is very important to check the signal waveform every time. So this is an example of pure silicon detector spectra of an equimolar sample of vanadium, manganese, cobalt, and copper. So this is a good spectra, as you understand. But the some circuit parameter is not good. Then the same sample you can observe just like this. So there's something wrong. You understand? And analog signal monitoring is always important. I'm sorry, Tibor Pap died last December because of the corona, but he said DSP, digital signal processor, is a kind of digital oscilloscope, and every time we must check, even we use the digital signal processor. So his words is very important. So this is another example. So this is measured by the germanium detector and analog amplifier. So here is the sun peak. You find here the sun peak has low energy tail. So if you measure this kind of spectra, the sun peak is always to the low energy tail, has a low energy tail, just like this. But if you use DSP, this is again the sun peak, but no tail, and the peak is quite symmetric. This is because there's some numerical algorithm in the DSP. So we must always check the both the digital signal and also the analog signal, or DSP spectra, and also the analog spectra, also analog waveform. It's very important. I'd like to skip the explanation of the sun peak. So sun peak is you can calculate just like this. There are box. The width is the shaping time, and how many balls photons into the box. You can calculate the counting rate dependence of the sun peak intensity. So I'd like to say about the proportional counter. The proportional counter is not used for the TXRF. And the proportional counter is usually used with wavelength dispersive spectrum. But this is quite simple, and we always know something about the proportional counter. So this is the monochromated vanadium K alpha measured by a proportional counter and a pulse height analysis. That means this is the EDX, energy dispersive spectra of proportional counter. That means proportional counter is a kind of EDX. And we can measure the X-ray spectra, energy dispersive X-ray spectra using a proportional counter. And if we can make lower the applied voltage. So at this time, I used 1,750 volts was applied to the proportional counter. But this voltage becomes lower if we can make the voltage of this make lower and lower. Then the energy resolution becomes better and better, and we can obtain the quite good EDX spectra only by the proportional counter. But it's a very strange that this is always measured monochromated titanium K alpha, and the titanium K alpha counting rate is 70 CPS or 1000 CPS or 130 CPS. So you can see here, this is a 5 volt line, and this is 10 volt line, and this is 0.5 volt line. So you can see that the peak is shifted to lower energy when the counting rate is high. So pulse height distribution of a proportional counter is changing as depending on the X-ray intensity. That means gas amplification is larger for low counting rate, and solid state detectors is more or less quite similar. But we can recognize, or we cannot recognize. It's very small, and mostly we cannot recognize, but quite similar. But when I talk about this in some X-ray company person, as far as I know, all the X-ray company persons know about this effect. But and they installs some kind of program changing the applied voltage or changing the window electronically. They installed the commercial machine. So this is if we set to the 0.5 to 5 and 5 to 10 windows, then if we measure the X-ray spectra, it depends on the window settings, just like this. So if we want to measure the accurate profiles of X-ray spectra, the window should be very, how to say, very carefully determined. And this is another example that K alpha to K beta intensity ratio. Also, it depends on count per seconds. So the weak peak, the window, this is enough. Was you must include the escape peak. But for strong peak, this is shifted, and it is out of the window. So this kind of thing is always very important. And I'd like to say about the background and thickness. So this is the thickness-dependent X-ray fluorescence intensity. So 0 to 100 micrometer thickness. The X-ray fluorescence intensity increase drastically. But over these 300 micrometer, it's almost constant. So if you analyze quantitatively the 100 micrometer or single one particle, and to determine its concentration, it is very difficult. This is probably the TXRF is how to say, very difficult for quantification. This is one reason. So noisy signal, it's sometimes very difficult to determine the background. Also, this is the SDD data, and this is energy of the characteristic line, and this is width at half maximum. As you see here, the energy and the width of the characteristic line is it's a linear relation. But as far as I know, the Niton company, when the detector, such as detector window was broken and they replaced the new STD, then they use about 1 week to memorize all the elements, line shapes, or maybe their data into the computer program inside the Niton handheld spectrometer. I guess this is the reason the quantitative analysis results is quite reliable for the handheld spectrometer. So I'd like to say about the wavelength dispersive X-ray spectrometer, or EDX. So wavelength WDX is used for process control in steel making recently. So this is an example. So here is the sample, and this is a steel sample, and this is X-ray tube, and here is the solar slit, Zora slit, and crystal, analyzing crystal, and detector. And this is another crystal, it's a curved crystal, and another curved crystal and detector. So as far as I know, in the steel company, 40 crystal spectrometers are installed in one single standalone spectrometer. So that means they can determine quite precisely the 40 elements quantitatively at the same time. But EDX is also used in a metal company, but only discriminate classification of iron scraps at most. EDX is not possible to use for the process control. The precision is completely different, and usually EDX is enough for our purpose, such as today we receive food analysis, and next day we receive some metal analysis or something like that. And the precision of WDX is usually quite better than EDX. But the precision of synchrotron radiation WDX is worse than tube EDX, as I shown you previously. This is, yes, this one, just like this one. So the choosing EDX or WDX depends on the sample preparation. If you analyze samples as received, you do not need wavelength dispersive spectrometry. So maybe this is the last part of my talk. Maybe I listed this reference in the leaflet of today's talk, and it is written, retracted article. So maybe most of you asked in your mind, so what the hell is this? So we submitted to the Journal of Analytical Atomic Spectrometry, and then it was published as the, how to say, just like this format. It's almost the same as the final form. And the first author checked the data, and he found the some standard deviation was some numerical error because of some computation. And he asked to correct the paper already published. Then the editor decided this paper should be retracted. But in this paper, we have many good ideas to reduce reduce the background or improve the signal to noise ratio, something like this. For example, USB connector generate strong noise, and we omitted the USB connector, and this is MOX-TEC X-ray tube old type, and we covered carbon tape and also the high purity silicon detector. It's very tedious to use liquid nitrogen and high voltage up to 1000 volts. But this is quite good signal to noise ratio. And finally, we get something like the previous this spectrum. And now the MOX-TEC X-ray tube becomes like this, and no need to use this cable, electric cable. And also this this controller is replaced by this small electric circuits. Then summary of my talk is, so sampling amount is very important for accurate and precise quantification. And electric circuit and terminator sometimes and signal should be checked every time. And SDD has individual characteristics, and how many X-ray researchers or companies memorize each SDD characteristics into the quantitative program. I'd like to know. The count per seconds dependent amplitude of proportional counter. X-ray companies know, but usually they do not open. But if we say, we ask, then they are how to say, quite open to us. So if we know, it's possible to know how to improve our spectrum. And the surface roughness, as I was a bad student, and then I know the surface roughness is important. And beam size and the quartz carrier shape is also very important. And EDXRF is enough when So the sample preparation, we do not control the sample preparation. So we must check the analog signal from time to time using a DSP as a digital oscilloscope. So thank you for your attention.
Thank you so much for this highly interesting talk and sharing your experience with us and reminding us all the critical steps that are involved before we end up with a quantitative results. I'm trying to switch on my video, but
Maybe
okay.
Christina Xray has some question.
Yes, exactly. I would like invite everyone to ask their questions. Christina, please go ahead.
Okay, thank you very much. So Jun, it was quite fascinating talk. I think you pointed out a lot of problems and which has to be considered. I have a problem because maybe I did not get the point. The topic of your talk was about the precision in TXRF. And you were talking about the problem of WD and the problem of ED and so on, but and rough surfaces and things like that. But I lost the connection to TXRF. Can you comment that?
Yes, TXRF. So the critical angle is very important. So only a very small amount of difference we lose the precision, and the surface roughness is also a very big factor, and the particle size, as you understand. And the most important, I'm now thinking, is the sample amount. So the TXRF, the sample amount is very small compared with usual X-ray fluorescence sample size. So that may be a big problem. And if we can make the beam size of the X-rays, it's usually we use 1 centimeter with the X-ray beam size when we use the laboratory TXRF. But if it becomes 3 centimeters or something, and we can make a homogeneous samples carrier surface, or it means homogeneous means such as you and Ursula tried the inkjet printer, such kind of thing is also quite a good idea. And so the homogeneous sample surface make improve the precision of the TXRF.
Yeah, so that the reflector, the sample reflector, has to have a polished, smooth surface. I think this is something which is obvious in TXRF. But where do you see a rough surface in TXRF, and where do you see these problems with the proportional counter and peak shifting? So I do not really see the connection.
Okay. So my talk is so many topics included, and the peak shift is also sometimes a very big problem, even for the SSD. It's a solid state detector of all type. And essentially, the counting rate for the SDD is quite similar. But the SDD, they use digital signal processor to compensate the high counting rate. And that means, how to say, if we want to analyze if we want to measure the X-ray intensity precisely, even if we use the SDD detector and the digital signal processor, the counting rate should be as small as possible, such as the total integrated intensity should be 10,000 counts per second or 1,000 counts per second or something like that, not 1 million. So such kind of thing is will help to measure the X-ray intensity precisely. This is my point.
So,
I'm sorry, I omit the.
And you properly, then these are things, this has to be considered by the producer of the TXRF spectrometers. And not by the user should be allowed to, that the producer is selling an instrument that fulfills the requirements, or not?
So the user, even the user, so the too strong X-rays, we avoid too strong X-rays. And so it's a trade-off. So if you want to detect the trace elements, the X-ray should be strong enough. But if you want to achieve the linearity of the linearity between the concentration and the X-ray intensity, you must use low counting rate. This is my opinion, not accepted, I'm not sure.
Okay, good, thank you.
I have one question.
Okay. You.
I have one question.
Yes.
Kaushik, myself, Kaushik. Sir, it's a very nice presentation, but I have one doubt that how the shape of the quartz reflector basically determine the accuracy or precision in TXRF. You have shown us one square shaped quartz reflector and one circular quartz reflector, and how the shape of the reflector basically decides the TXRF quantitative capability or quantitative analysis.
I cannot understand where your question, but the sample carrier shape of square type and disk type.
Is there any difference in accuracy or precision in between these two type of shapes, like square type and circular type, and why it is so?
Yes, because the X-ray is hitting the edge of the disk shape sample carrier sometimes. And if the geometry is not properly adjusted, the scattering X-ray will interfere the measurement. And once I try to change the square type sample carrier every 90 degrees rotated, then we found the different X-ray spectra. So such kind of thing is also very important for the quantitative analysis. So that we don't know the answer to this problem.
Thank you, sir.
So I understood regarding the shape that it was that the scatter at the edge of the carrier was the problem. Is that correct?
Yes, it's correct. So the disk shape, sometimes the X-rays hit the edge of the carrier, but the square shape is it is attached very close to the X-ray tube, so no problem, I think.
But this problem may arise when the beam size is very broad enough. I thought so. For small size beam, I think this problem wouldn't occur. That is my thought.
Yes, but if the beam size is small, then the inhomogeneous sample surface effect we can is interfering the X-ray spectrum.
And do you think that so for the synchrotron setup, and I don't know if it's in the commercial instruments as well, there's this Tantal Edge that prevents the beam from hitting the edge? Is this something that could prevent that, or?
So your question is again the
so
sample
to put a tantalum edge into the beam path, so to prevent the beam from hitting too farther downstream on the carrier, so that
yes, if the some slits in the beam line, sometimes the interference of the edge to the X-rays will make the X-rays much broader, and but maybe I'm not sure, but we can sometimes observe some interference effect, such as it's I forget the English term. So some interference we can observe when the X-ray is totally reflected on the flat surface. So so the X-ray is not straightly limited by the slit of the beam line, and maybe straight line is always a big problem in the synchrotron beam line.
yeah.
Isn't it?
Thank you. Thank you. We already have a vivid conversation. Are there more questions? Are there more questions from the audience? So you are welcome to write your questions also into the chat. Then I can read that out if your mic is not working. Okay, I don't see any more questions, and I think we are already well in our time frame. So I would like to thank you again. Thank you so much to give this very first talk in our TXRF Journal Club. And before we all turn back to our daily duties, I like to announce the next TXRF Journal Club speaker, which is Professor Peter Browacek from Vienna University of Technology. And he will present his talk on June the 24th, again at noon Berlin time and 7 p.m. Tokyo time. And yes, I wish all of you good day, a good night, and be safe. And yeah, let's meet again then in about 4 weeks from now.
Okay, thank you very much.
Thank you.